Okay, hi, my name is Armisha Sonia, and today I will be presenting about rotational motion and its real-life relation. First, let's look at the introduction. Rotational motion is the movement of an object that spins around an fixed axis. Every point on the object moves in a circular path. To describe rotational motion, we use several important concepts such as angular displacement, angular velocity, angular acceleration, torque, and moment of inertia. Torque is the rational equivalent of force because it causes an object to rotate. Meanwhile, moment of inertia represents an object's resistance to change in its rotational motion. Another important concept is angular momentum, which is the product of moment of inertia and angular velocity. According to the law of conservation of angular momentum, it remains constant when no external torque acts on system. Okay, now let's see how rotational motion is applied in sports science. A good example is a figure skater. When the skater pulls their arm inwards, their moment of inertia decreases, causing them to spin faster. This happens because angular momentum is conserved. Similarly, divers also use this principle. By changing their body position in the air, they can control their rotation and perform twists and spins before entering the water. Next, rotational motion plays an important role in vehicles mechanics. Bicycle wheels and car tire rotate continuously to allow smooth movement. In engines, flywheels store rotational energy and help stabilize speed and improve efficiency. These examples show that concepts such as torque and moment of inertia are essential in transportation system. Okay, finally, rotational motion can also be seen in everyday tools. For example, using a longer spanner makes it easier to loosen a tight bolt because the larger radius produces greater torque. Another example is a door handle. It is placed far from the hinge so that less force is needed to open the door. These simple examples show that rational dynamics is not only a physical concept, but also an important part of our daily life. That's all from me. Thank you.
Hi, today I will be presenting about specific physics principles involved. The rotational dynamics topic involves four main physics principles, which is moment of inertia, torque, angular momentum, and the conservation of angular momentum. First, let us talk about moment of inertia. Moment of inertia is the rotational equivalent of mass in linear motion. Moment of inertia can be defined as the tendency of a body to resist angular acceleration. It measures how difficult it is to change an object rotational motion and depends on how the mass is distributed around axis of rotation. There are a few factors that influence moment of inertia, which is mass, distribution of mass, and axis of rotation. The formula for moment of inertia is I equals to mr squared, and the unit uses was kgm squared. Second, let us talk about torque. Torque is the tendency of force to rotate an object about axis of rotation. To make an object start rotating, a force is needed. The position and direction of the force matter as well. The greater the torque applied, the faster the object rotates. The unit used for torque is nanometer, and the formula for it is I times with alpha. Third, we will talk about angular momentum. The angular momentum of a rigid object is defined as the product of the moment of inertia and the angular velocity. Angular momentum describes the amount of rotational motion an object has. An object with a larger moment of inertia or higher rotational speed has greater angular momentum. It is similar to linear momentum and is subject to fundamental constraints of the conservation of angular momentum principle if there is no external torque on the object. The unit used for angular momentum is kgm squared per second, and the formula is I times with omega. Lastly, we will talk about conservation of angular momentum. The law of conservation of angular momentum states that the total of angular momentum of a rotating rigid body remains constant if the net external torque acting on it is zero. This explains why changing the distribution of mass changes the rotational speed. In the absence of an external torque, angular momentum is conserved. Without further ado, we will talk about the daily life application of these four main physics principles. So, every day on daily basis, we will open a door. When opening the door, we push near the handle instead of the hinge because a larger distance from the pivot produces greater torque, making it easier for us to open a door. Next, when we're using a wrench, a longer wrench will produce greater torque, allowing us to loosen or tighten bolts with less effort. And lastly, figure skating. Most figure skater spins faster by pulling their arms inward because this reduces the moment of inertia and angular momentum is conserved. And that is all for me. I will pass this presentation to my next member. Thank you.
My name is Josephine Isabel Milicia Anujan Bosco, and I would continue on how does the system work based on rotational mechanics or thermophysics principles. The first example is opening a door. So a door rotates about a fixed point located at its hinges. Now if we push right at the hinge, there's nothing happens because the hinge produces no rotations. But if we push near the handles, which is far from the hinge, it suddenly swings open easily. And that's because torque is actually depends on how far the force is from the pivot point. The farther out we push the door, the more perpendicular the push is, the more torque we generate, which can describe by the formula tau equals to Fr sine theta. So for the second example is using a wrench. The same concept as opening the door. The bolt acts as the pivot point. A longer wrench gives more distance from our hands to the bolt. So the same force produces more torque, which is exactly why mechanics use longer wrench for stubborn bolts. Once the torque is large enough to overcome the torque's resistance, it causes angular accelerations, which allowing the bolt to loosen or tighten. So for the third example is figure skating. It's a little bit different from the first and the second example. It's not really about torque, but it's involved more about conservation of angular momentum. When a skater spins, there's basically no external torque acting on them, so the angular momentum stays constant, which can be described with the formula L equals to Rw. When they pull their arms in, their mass is closer to the axis, which lowers their moment of inertia. Since angular momentum has to stay the same, the spin speed has to go up to compensate. That's why pulling the arms in makes them spin faster. Next is how are these physics concepts applied in the systems. So for the opening the door, formula torque equals to force times the distance times the sine of the angle. The bigger the distance from the hinge, the bigger the torque, which then drives the angular accelerations through torque equals to I alpha. For the wrench, the same formula applies. Increasing the distance by using a long wrench boosts the torque. Once the torque is large enough to overcome the bolt's resistance, angular accelerations occurs, allowing the bolts to loosen or tighten with less effort. For figure skating, the formula L equals to I omega. Since angular momentum has to stay constant during the spin, and the moment of inertia decreases as the arms pull in, the angular velocity has to increase to balance it out. That's the conservation's law at work.
Hi, my name is Vanessa Ivy Antonio, and I will present part what physical processes, mechanisms, or equations are involved. So, the title for this slide is Torque and Angular Acceleration, Torque Generation. The process is rotational force application. When a force is applied at a perpendicular distance from a pivot point, it generates torque. This serves as the rotational equivalent of linear force. It is the exact mechanism used to overcome static resistance when loosening a bolt with a wrench or pushing a heavy door open from its edge. So, this is the second topic under what physical processes, mechanisms, or equations are involved. There is rotational inertia and mass distribution. The process is mass distribution's control. An object's resistance to changing its rotational speed depends entirely on how its mass is distributed relative to the axis of rotation. Because mass distributed further away quadratically increases resistance, the system's inertia can be dynamically altered just by shifting its physical shape. So, this is the last topic under what physical processes, mechanisms, or equations are involved. There is conservation of angular momentum, conservation laws. The process is angular velocity compensation. In an isolated system with no external torque, the total angular momentum must remain constant over time. If the moment of inertia changes, the angular velocity must dynamically adapt to keep the system balanced. For example, When a skater starts to spin with their arms and legs extended outward, their mass is far from the axis of rotation. This creates a high moment of inertia, resulting in a slower, controlled spin speed. Second example, when a skater pulls their arms and legs tight into their chest, they instantly reduce their mass distance from the axis. This creates a low moment of inertia. To conserve angular momentum, their spin speed instantly rockets upward, making them spin incredibly fast.
Good days, my name is Aisha Fika binti Yaakob and my student ID is 2025859554. Now, let's explore the real-world application of this concept. What outcome or effect can be observed from this system? We can break this down into three examples. Open a door using a wrench and figure skating. First, let's look at opening a door. To maximize torque, you want to apply force as far from the pivot point as possible. Because of this rule, all commercial and residential doors are intentionally designed with their handle placed at the edge as far from the hinge as possible, making them much easier to push or pull. Next, to think about using a wrench. When you apply a heavy amount of torque, the physical outcome is either the tightening or loosening of a bolt. However, engineers always have to consider the material limits. If the applied torque exceeds what the metal can handle, it will lead the material failure and cause the bolt or the tool to snap. Finally, let's look at the figure skating. When a skater pulls their arm inward, their angular velocity spikes, causing them to spin incredibly fast. A major observable effect of this high-speed rotation is the strong outward pull felt by the skater. Their loose clothing and even their blood flow are forced outward due to centripetal acceleration. These three examples show how rotational mechanics and torque operate in everything. Next, what happens when a door hits a door stopper? When the door reaches its maximum angular displacement and strikes the stopper exerts a strong opposing force. This instantly drops the door angular velocity to zero, effectively preventing any damage to the wall. Second, let's look at the range. When we apply a linear force by hand over the rotational distance, we can measure the physical displacement. This gives us rotational work done. An observable effect of this process is the heat generated by friction between the bolt threads as they tighten. Finally, how does the figure skater slow down? To stop spinning, the skater must exit their arm outward. This increases their moments of inertia, which act as a natural braking mechanism to reduce the angular acceleration. After slowing down, they can easily use frictions against the ice to come to a complete stop. In summary, rotational mechanisms bridge theoretical physics with real-world outcomes. By balancing core principles like moment of inertia, torque, and the conservation of momentum, we can directly observe and control physical effect in every applications. Such as, we can show this when maximizing torque with door handles design, safely bringing angular velocity to zero using door stoppers, and creating rotational work done with a wrench. We also observe it in figure skating where changing the moment of inertia allows a skater to control the high speed spin and come to complete stop. Ultimately, this practical outcome proved that rotational dynamics is absolutely essential for both intelligent engineering, design, and mastering complex physical motions. That's conclude our presentations today. Thank you very much.